Hey guys, Ms. Peterson here, and today what we're talking about is chemical reactions. We're going to go over how to predict products of a chemical reaction and balancing reactions. Okay, so these are our chemical reaction notes. I'm going to keep doing them Cornell style like I normally do, which will not look that pretty on here, but that's okay. Okay, and the first question I have for you is, what is the law of conservation of matter? Okay, now this is a fundamental law of the universe. Okay, basically, we can't create things. Everything that we have has always been around. And we learned this back in the beginning of the year when we were talking about where all the elements come from when they're formed in stars in the galaxy. We've talked about it with the carbon cycle and how the carbon atoms that are in our atmosphere and piling up there just came from the geosphere, from those fossil fuels trapped deep in the earth. Okay, that is the idea behind everything we do in chemistry, is understanding how that matter changes. But we're never creating anything new. We're just rearranging and moving around things that already exist. Okay, so matter, by matter, I mean atoms mostly, okay, are never created nor destroyed, only changed. Okay. In terms of our chemical reactions, what this means is that the atoms in our reactants always are the same as the atoms in our products. Okay? We're never going to come up with atoms out of nowhere. Our atoms are never going to disappear on us. If they're there, they're there. They need to be on both sides of the arrow, the before and the after. So, speaking of our chemical reactions, how do we balance a chemical reaction? We've done this a little bit already in class, but I'm going to give you a foolproof technique so that if you are struggling, this is a way that you can definitely balance reactions, even if you're not so math-minded, because we aren't. So, how do we balance a chemical reaction? Okay. So, the main thing that you guys need to remember when balancing your chemical reactions is you are not ever going to change the chemical formula. Okay? The chemical formula describes that element. It is the way that they bond to become stable. Okay? If it's carbon dioxide, it's always CO2. If it's sodium chloride, it's always NaCl. If it's magnesium hydroxide, it's always MgOH2. That's how they bond. That's how they fill up that outer shell of valence electrons. It's how they become stable. So we're only going to be changing coefficients when we balance our chemical reactions. Okay? So we change coefficients so the equation follows the law of conservation of matter. Okay, aka the number of atoms of each reactant equals the number of atoms of each product. Okay, you're not pulling things out of nowhere. So, I'm going to show you guys an example, and then I'm going to show you guys a little trick. So, say I was looking at the decomposition of aluminum oxide. Aluminum oxide is Al2O3. Okay, now it is it decomposes into its parts. It is made of aluminum and oxygen. Okay? Oxygen is one of those diatomics. It never exists by itself. It's always going to be O2. Little side note, if you want to memorize them, okay, the diatomics, the mnemonic is Hunkelbrief. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Hunkelbrief. Okay, those ones in nature, in their elemental state, they always exist bonded to each other. Okay, now, if you are looking at this reaction and you're going, oh, well, I have a 2 there, so I put a 2 there. I have a 3 there. Oh, but I only have 2 there. So how do I balance a 3 and a 2? I put a 2 there and I put a 3 there. You're good. You can balance a reaction. But if you're not quite there yet and you're like, what are you doing, Miss Peterson? I haven't understood this at all. Okay, I'm going to show you guys a trick I call the brick method. Okay, so right now we are looking at an unbalanced reaction. So one way we can balance it is I'm going to draw a line down the middle of my page. And I'm going to draw bricks for each of my compounds. So aluminum oxide is a compound, and it is made of 2 atoms of aluminum, okay, Al2, and 3 atoms of oxygen, O3. And that's my brick of aluminum oxide. Aluminum is just elemental aluminum, so it's just Al. Oxygen gas is 2 oxygens bonded together. Okay? Then you start canceling things out. So this aluminum cancels out with this aluminum. Okay, I'm canceling out if they're on the same on both sides of the arrow. This oxygen cancels out with this oxygen. This oxygen cancels out with that oxygen. And then I'm going to add bricks until everything cancels out. Okay, so you have the bricks for compounds, and then you add bricks until everything cancels. Okay, so I still have one aluminum that still isn't canceled, so I can add another aluminum brick. And that cancels, that cancels. But now notice the problem. I don't have any O bricks. I don't have an O brick just by itself. I only have O2. So I have to add a whole other O2. But notice, cool, that cancels out that one. But now I still have another oxygen left over on this side. So unfortunately, on the reactant side, on the left side, I only have aluminum oxide bricks. Okay, that's the only compounds that I have. So I have to add a whole other aluminum oxide. Okay, and then this oxygen cancels out with this one. Now I have 2 more aluminums, so I'm going to add 2 more aluminums. Aluminum, 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 and now I have 2 more oxygens, so I'm going to add 2 more oxygens. And 1, 1, 1, 1. Now, if you look at this, you can see I had 4 aluminums total and 6 oxygens total. Okay, how many atoms of each I had? And over here, I had 4 aluminum and 1, 2, 3, 4, 5, 6 oxygen. So it all checks out. It is all balanced. Okay, and then the number of bricks that you have becomes your coefficients. Okay, oopsies, I erased my line. So I ended up with 2 bricks of aluminum oxide, so 2 Al2O3, 4 bricks of aluminum, and 3 1, 2, 3 bricks of oxygen gas. Okay, so then the number of bricks become your coefficients. Okay, another little trick when doing this, okay, is that whenever you have a polyatomic, you can put it as one brick. So if you have a polyatomic that stays, if it's a reactant, it stays a reactant. If it's a product, it stays together, like it's nitrate here and nitrate there, you can treat it as one brick. Okay, so that's a little trick if you're still struggling on these balancing reactions. If you can do it in your head and figuring out the math, how those work out, then keep doing it that way. As long as you get it balanced, doesn't make a difference to me. Okay, cool? Okay, cool. Now, we're gonna go through and do short little blurbs about each of the 5 main reaction types: synthesis, decomp, single replacement, double replacement, and combustion. And we're gonna look at some examples, and I'll give you guys a little bit of hints and tips on how to predict the properties of these things. Okay? So, scroll on down here. Okay, so first off, the writing gets messy on here, so I'm just going to write it with the type of reaction. First off is synthesis. So a synthesis reaction is a reaction in which 2 or more small elements or compounds come together to form one product. Okay. Sometimes you'll see these in like different types of notation. So basically it's when you got one thing bonding with another thing to form one thing. So they were separated, they were 2 separate compounds, and then they joined together. Okay. For these, predicting the products of these, it's pretty easy. Normally the product is going to be ionic, and then you just follow your ionic naming things to figure that out. Okay, so let's look at an example. Okay, let's look at magnesium solid reacting with oxygen gas. Okay, so the magnesium is my A, and my oxygen is the B. So now all I need to figure out is, okay, if I have magnesium and oxygen, put them together, I have magnesium oxide. Okay, so magnesium reacts with oxygen gas to produce, and when you put magnesium and oxygen together, you get magnesium oxide. Okay, but what's the formula of magnesium oxide? Well, that's a metal. Magnesium's a metal. Oxygen's a nonmetal. So we know it's going to be an ionic compound. So if we remember our ionic naming rules, magnesium has 2 valence electrons, so it's a 2+. Where oxygen, oxide, has 6 valence electrons, it tends to gain 2 and be a 2-. So magnesium oxide will just have a 1-to-1 ratio there. It'll just be MgO. Okay. Now, we need to balance it. Okay. This one I'm just going to go ahead and balance it in my head. In another one, in the decomposition one, I'll go ahead and use the brick method for you. Okay, so I have 1 magnesium and 1 magnesium. That checks out. 2 oxygens, only 1 oxygen. So I put a 2 out front there. But now I have 2 magnesiums. So I'm going to put a 2 out front there. Okay, cool. Okay, cool. Next, the opposite of a synthesis reaction is a decomposition reaction. Okay, so a decomposition reaction is one where you have a single compound breaking up into smaller parts. So a single reactant, breaking up into smaller parts. Okay, so basically it's the opposite of a synthesis, is where you have something together and then it separates. Okay, an example of this one that we saw in class was the decomposition of sugar. Okay, remember when we did that sugar snake reaction and it grew and formed that elemental carbon? That was a decomposition reaction. So let's go ahead and try to write the words for it. So sugar decomposes into carbon and water. Okay, that's how we would say that reaction. Now let's go ahead and write it. Sugar is C6. Oops, nope, we did it with table sugar, not glucose. C12H22O11, and it decomposes into carbon, which is just solid, and water, okay, which was mostly a gas because it was a really exothermic reaction. Right? Don't worry too much about the phase symbols though. As long as you can predict what products they are, I'm not going to worry too much about that. And I said that I was going to do the bricks for this, but I don't want to draw 12 carbon ones, so I'm not going to. Okay, so we had 12 carbons here, so we have 12 carbons there. We have 22 hydrogens and 11 oxygens, so I'm going to need an 11 in front of my water. Okay, and that is a decomposition reaction. Okay. Now let's go to our ionic ones, okay? Our reactions that occur mostly with ionic compounds. We're going to look at single and double replacements. Okay, so a single replacement is a reaction in which the atoms of one element replace the atoms of another in a compound. Okay, so in this one, you can kind of, in symbol notation, we have some element A and some compound, I'm going to call it BC. And then it reacts, and the A is like, I'm going to take your place, B, forming AC and leaving the B by itself. Okay? And it's always going to be typically ionic, where you have a metal replacing a metal or a non-metal replacing a non-metal. Okay? It won't be the other way around. An example of this one that we saw in our lab was when we dropped aluminum into copper chloride. Okay, so we had copper chloride, which is CuCl2, reacting with aluminum. Okay, oopsies, I wrote that backwards. I'm going to write that the other way for you so it matches the little ABC notation that we wrote. Okay, there's no right or wrong way to write it. It's just however you prefer. So we have aluminum reacting with copper chloride. Now, what are going to be the products of this reaction? Okay, well, I have aluminum and copper chloride. I'm going to go ahead and write the words because it might make it easier for us. Aluminum and copper. It has 2 chlorines, so it's going to be copper 2 chloride. React to form Well, the aluminum was by itself and the copper was with the chlorine. So when they react, the aluminum and the copper switch places. So then we're going to have aluminum chloride and copper. Okay, so now what's the formula of aluminum chloride? Well, aluminum has 3 valence electrons, so it's going to be a 3+. Chlorine is always a 1-, so I'm going to need 3 chlorines to balance out that 3 copper. So aluminum chloride must be AlCl3. And then we just leave the copper by itself. Okay, but I'm not done yet. This reaction isn't balanced. Okay. If you can see how to balance it, great. I'm going to go ahead and do another example of the brick method to show you guys how that works. So draw my bricks, my aluminum, my copper, chlorine, my aluminum chloride, 1, 2, 3, and my solid copper. Okay. Then I start canceling out. 1 aluminum, cool. 1 copper, cool. 2 chlorines, ah, dang it, got another chlorine left. So on the left side, the only way I can get another chlorine is to add another copper chloride. Cu, Cl, Cl. Okay, then the chlorine cancels out with that. But now I have another chlorine and another copper. You probably saw where this was going with the 2 and the 3. So now copper, and I'm gonna need another copper. And copper, and I still have that 1 chlorine left, so I'm gonna have to add another whole aluminum chloride. Okay, so now that chlorine reacts with that chlorine. Oops, sorry, I forgot to change my color. Okay, I have another aluminum, so I'm gonna need another aluminum over here. Okay. So then the aluminums cancel out, but now I still have 2 chlorines. So I'm gonna have to add a whole other copper, chlorine. Okay, so these 2 chlorines cancel out with these 2 chlorines. I have 1 more copper, and copper cancels out with copper. And then my number of bricks become my coefficients. So it's gonna be 2, 3, 2, 3. Okay, cool. Okay, cool. We're almost done here. Just 2 more types of reactions. Okay. So the next one is a double replacement. Okay, remember this one's white swap. So a double reaction is one in which the atoms of 2, this one only happens with ionic compounds. So ionic compounds switch places. Okay. So you had some compound, we'll call it AB, reacting with some compound CD, and they flip-flop paces. So this one goes with this one, and this one goes with this one. So it'll be AD plus CB, because we still always want to write the metal first. Okay, so let's look at an example in this one. Okay. Say we have, let me think, we're going to have calcium carbonate, which is CaCO3. Oops, I wanted to actually write it out. Okay. Calcium carbonate reacts with, let's do magnesium hydroxide, why not? magnesium hydroxide to form, and they switch places. So it'll form calcium hydroxide and magnesium carbonate. Okay, so now we just need to figure out the formulas of all of these things. Okay, so calcium is Ca2 plus. Carbonate is one of those polyatomics, CO3 2 minus. So calcium carbonate is CaCO3. And it's going to react with magnesium, which is a 2 plus. Hydroxide is OH minus, again, polyatomic, you just got to memorize it. So MgOH, oops, that was bad parentheses, 2. Okay. So when they react, they form calcium hydroxide. So I'm going to have calcium, which is the 2 plus, with the hydroxide, which is 2 minus. So that is CaOH2 and magnesium carbonate. That one's a 2 plus and a 2 minus, so I'll just be a 1-to-1 ratio. Oh, oopsie, my calcium hydroxide was wrong. I was testing you guys. Did you get it? Okay, calcium is a, oh, no it's not. Why am I going crazy here? Oh, okay. Sorry, don't know why I did that. Calcium hydroxide and magnesium carbonate. Okay, because they are a 1-to-1 ratio. And if I look, cool, that one's already balanced. So I don't even have to do anything. Okay, last type of reaction. Last one, we're almost done. Thanks for staying with me, guys. Okay, it is a combustion reaction. Okay, so combustion reaction, think fire, explosions. No, I mean, but really, it's anytime you have something which is normally a hydrocarbon, or one with some oxygens in there, reacting with oxygen gas to produce carbon dioxide and water. Okay, those are always the products. It's always going to be some chemical A reacting with oxygen gas to produce carbon dioxide and water every single time. Okay, so let's look at an example. Let's look at, not methane, we've done methane. Let's do propane. Okay, propane is C3H8. Okay, so if it combusts, it reacts with oxygen gas to produce carbon dioxide and water. Okay, and then we have to balance it. So 3 carbons here, 3 carbons there, 8 hydrogens here, 8 hydrogens here, and then that brings me to 3 plus 2, that's 6 oxygens from that one, 4 oxygens from this one. So I have 10 oxygens on my product side. So I'm going to need 10 on this side. So I need to put a 5 there. Okay, cool. Go ahead and try your skills at the FET and on your homework assignment. And I will see you guys after break. Okay, bye.